Hello everyone, today we are again with another video on shuffle fundamentals and right path. Before we start, let me say something bold. Most Spark performance problems are not because of joins. They are because of shuffle. So if you deeply understand shuffle, how it writes, spills, reads, and transfers data, you can debug almost any Spark job. Today we are not just defining shuffle, we are understanding how Spark behaves internally. So the question arises, what is shuffle? Shuffle is the process where Spark redistributes data across executors. But that simple definition hides a lot. When shuffle happens, data stops being local to one executor. It must move across machines in the cluster. That means it must be sorted. It may spill to disk. It must be written to shuffle files. It must travel over the network. It must be fetched and merged. So shuffle is not just data movement. It's a full cluster-level coordination event. So the question arises, what triggers shuffle? Shuffle happens when Spark cannot compute the result within the existing partition structure. For example, if you do a group by based on a key, Spark must bring all records of the same key together. But those records may exist in different partitions. So Spark has no choice. It must redistribute data based on that key. That redistribution creates a wide dependency. And wide dependencies create shuffle. This is why operations like joins, group by, distinct, repartition, and order by often trigger shuffle. Now Spark divides execution into stages. As long as transformations are narrow, Spark can pipeline them in one stage. But the moment a shuffle appears, Spark must stop and create a stage boundary. So then the question comes, why does it have to stop? Because data must first be fully written before it can be read by another stage. So shuffle creates a stage boundary. Before shuffle, it's the map stage. After shuffle, it's the reduce stage. This is a physical execution separation, not just a logical one. In a narrow dependency, one output partition depends on a small number of input partitions, often just one. Spark can process these transformations locally without moving data across executors. Examples include map, filter, and flat map. In a wide dependency, one output partition may depend on data coming from many input partitions. That means Spark must pull data from multiple executors. That is where network transfer begins. And that is where shuffle cost begins. Now let's zoom into what happens during the shuffle. Each map task processes its own partition. After applying transformations, Spark prepares the data for redistribution. But here is something very important. Spark does not immediately send data over the network. Instead, it organizes and sorts the data locally first. So then you may ask why. Because reducers expect data grouped by partition and organized properly. So the map side is responsible for preparing shuffle data correctly. Modern Spark uses something called sort-based shuffle. On the map side, data is first grouped by target partition ID. Then it is sorted within those partitions. After sorting, Spark writes one consolidated data file and one index file. Each map task produces exactly one shuffle data file. It is not one file per reducer. The index file contains offsets that tell reducers where partition data is located inside the shuffle data file. This design reduces file explosion and improves efficiency. Now let's talk about memory. Sorting and buffering require execution memory, but memory is limited. When the in-memory buffer crosses a threshold, Spark spills data to disk. Spilling means writing partially sorted data to disk to free memory. This prevents executor crashes. However, it increases disk I/O, so spilling is a safety mechanism, but it comes with a performance cost. If multiple spills occur, Spark cannot leave them as separate files. It must merge them. This is essentially a merge-sort operation. All spill files are combined into one final sorted shuffle data file. This merge step consumes CPU and disk bandwidth. That is why the shuffle write phase can become CPU intensive. After merging, the final shuffle files are created. Each map task creates one shuffle data file and one shuffle index file. Reducers later use the index file to locate specific partition data. They do not scan the entire file. They jump directly to the required byte offset. This makes shuffle read efficient, at least structurally. Now comes the reduce side. Each reducer is responsible for one partition. But here is the important part. If you had 200 map tasks, each reducer may need to fetch its partition data from all 200 map outputs. That means potentially 200 network fetch operations per reducer. This is why shuffle red is heavily network dependent. If the network is slow, shuffle becomes slow. In Spark UI, you will often see a metric called fetch wait time. That metric tells you how long reducers are waiting for data. Shuffle is expensive because it touches every major resource in our cluster. CPU for sorting and merging, memory for buffering, disk for spill operations and file writing, network for data transfer. No other Spark operation stretches the cluster quite like shuffle. That is why performance tuning often means reducing shuffle. When debugging Spark jobs, always inspect shuffle metrics in Spark UI. Look at shuffle or write size. This tells you how much data was written. Look at shuffle read size. This tells you how much data was fetched. Look at spill metrics. These tell you how much overflow occurred. Look at fetch wait time. This tells you how much time reducers spent waiting for data. These metrics help you identify the bottleneck. Shuffle is not mysterious if you know how to read the UI. Now imagine one key has 10 gigabytes of data. Other keys have only 20 megabytes. One reducer will become overloaded. Other reducers may finish quickly. But the Spark job finishes only when the slowest task completes. That is data skew. Data skew does not increase total data volume. It destroys parallelism. We covered this in detail in a previous video. You can have a look at that as well. Modern Spark introduces something called Adaptive Query Execution, or AQE. AQE analyzes shuffle statistics after a stage completes. Based on actual runtime data, it can reduce shuffle partitions. It can split skewed partitions. It can even change join strategies. Shuffle is no longer completely static in Spark 3.x. It can adapt at runtime. We covered AQE in detail in a previous video. You can refer to that video as well, especially for interviews. As engineers, we should think before writing code. Can I filter earlier? Can I reduce partitions? Can I aggregate before a join? Can I broadcast a smaller data set? Shuffle reduction is performance engineering. The less unnecessary shuffle you create, the faster your jobs usually run. Joins are deeply connected to shuffle. If both tables are large, Spark performs a shuffle-based join. That means both sides redistribute data using the join key. Stage 1 performs the shuffle write. Stage 2 performs the join execution. If one table is small enough, Spark may use a broadcast join and completely avoid shuffle. So if you understand shuffle internals, you understand join behavior. Now let's visualize what is happening. Before shuffle, data is distributed across partitions. Each partition lives on some executor. Now imagine we want to group data by key. The problem is simple. All records with key equal to 1 may be spread across multiple partitions. Spark cannot compute the aggregation unless these records are brought together. So what does Spark do? It redistributes data. Every record is reassigned to a new partition based on its key. Typically, Spark uses a hash function. After shuffle, all records for key 1 land in the same partition, so all records for key 2 land in another partition. Notice something very important. There is no data duplication. No data is lost. Data is simply reorganized. That is shuffle. It is not magic. It is not random. It is deterministic redistribution. And this redistribution is what triggers everything we discussed today. So far, we have focused on the shuffle write path, sorting, spilling, merging, and creating shuffle files. But writing is only half the story. Now imagine this. If you have 200 map tasks and 100 reduce tasks, each reducer may need to fetch data from all 200 map outputs. That means hundreds of remote fetches across the network and across machines. This is where many real production failures happen. Fetch failures, timeouts, executor losses, external shuffle service issues, block transfer problems, network overload. In the next video, we will go deep into the shuffle read path. We will discuss map output tracker, block transfer service, remote fetches, fetch failures, network overhead, retry logic, external shuffle service, and why many Spark jobs fail during shuffle read rather than shuffle write. If you truly want to debug Spark like an architect, you must understand what happens after the files are written. Thank you for watching. See you in the next video. And as always, do share your thoughts in the comments.